Hello, dear students. So, to continue from where we stopped last time, we are still studying the medium access control methods as part of the functionality of layer 2, the data link layer. And we studied already the method called Aloha, and then we looked at the carrier sense multiple access methodology. We looked at the different types of the classical carrier sense multiple access. So we looked at carrier sense multiple access persistent, and then the non-persistent, and then within the non-persistent, we looked at the one persistent and the p-persistent methods. Now, as a modification for carrier sense multiple access, the standardization committee, and particularly inside the IEEE, came up with an added functionality, which is the collision detection. To describe the rationale behind this added functionality, in the previous methods that we discussed, whenever a collision happens, for example, a packet transmission from two different nodes happens at the same time, the whole duration from the start of the transmission here until the end of the transmission of the other packet here, this whole duration is wasted because both nodes will continue the transmission until the end of their corresponding packets, which means that this whole duration is wasted because of a collision that happens in the middle here. Now, in order to minimize the wasted time, which means enhance the efficiency, the collision detection mechanism ensures that at the point where the collision happens, which is right here, or let's say at the point where the collision detected, which is kind of at the start of the collision here, both nodes will stop transmission at the same time, which means now that you have reduced. So once the collision is detected, hence the name collision detection, both will stop transmitting, and this would reduce the wasted time to be the green one that we see here. Now, reduction of wasted time means better efficiency, okay? So let's look at the steps. The steps says that if the medium is idle, transmit, which we know. If the medium is busy, continue to listen until the channel is idle, then transmit. This is the non-persistent method. If a collision is detected during transmission, cease transmitting. That's the part that we described here. So stop the transmission at that point from both nodes or from all the nodes that are colliding together. And by the way, this detection cannot be done in wireless. It can only be done in wired. And this protocol is actually implemented in the Ethernet, the wired Ethernet, okay? And then after the collision and after the cease of the transmission, for the non-persistent, if you remember, wait a random count of time and repeat the same algorithm again. So this is the SYSMA non-persistent that we studied earlier, but added to it the collision detection mechanism, okay? Now here is a time sequence diagram that shows the carrier sense multiple access collision detection and the Ethernet protocol, as we mentioned. So you have T0, node A begins transmission, right? So this is node A, and it starts transmission, right? And at T0 plus some tau minus epsilon, so at a different time, node B begins transmission, right? Those take some time until you reach a point where, so the data is coming from A, now B started transmission right now, so this line is node A, this line is node B. Then at some point, right, the collision happens, okay? And now we can see that we will detect the collision whenever one of the transmitting nodes hears the other one during its transmission. So in this case, it's assumed that this finishes sending this before receiving this, so the collision is not detected here. The packet is traveling. At some point, this signal will reach point A. When it reaches point A and A is still transmitting, collision is detected here. Both nodes will stop transmission. In this case, it's actually node A because B has already stopped earlier, right? So this shows you just the sequence of things as they happen. Okay. Now, for the carrier sense multiple access collision, detection, we can see the different performance. Again, we don't have an equation for the performance here, but we can see a plot of that, okay? And we can see that the throughput is getting better as we change the parameter alpha. Remember what was alpha? It's the propagation delay divided by the transmission delay, right? So this is the average transmission delay of a packet, and this is the average propagation delay of the packet. And as the propagation delay becomes larger than the transmission delay, this means that the possibilities of collision gets less and less, because nodes finishes transmission before they can hear the transmission from other nodes. So you get a better performance. If you have alpha, which is closer to 1, the performance drops down. So it's better in carrier sense multiple access, as we see, to ensure that this parameter is a very small parameter, right? Again, having this equal to 0 means simply that there is no propagation delay, right? But typically, yeah, so sorry, to explain why when we have this very small, the propagation delay is much smaller than the transmission delay, which means that you can detect collision as soon as it happens. So you don't waste a lot of time transmitting while a collision happens later after a long time of transmission, which means more wasted time. So this explains why this looks the way we see it right now. Okay, for wireless devices, all terminals listen. So again, for wireless devices, we said that the collision detection is not possible. So what happens in the 802.11 that we use, which is the Wi-Fi? In that case, they use something called collision avoidance. So if I cannot detect collision, I will take extra measures to avoid the collision, which means I will try to reduce the probability of collision. And looking at that method, so let's see how it works. So all terminals listen to the same medium, and that's similar to the SISMA CD. So everyone is listening. If a terminal is ready to transmit, it senses the medium. If the medium is busy, it waits until the end of current transmission. And then, so if it finds the medium busy, okay, remember at this point, probably there is more than one node that needs to transmit. So if it finds the medium busy, it will wait until it becomes available, so until end of the current transmission, and then it adds another wait for an additional predetermined time called the distributed interframe spaces, DIFS. Then it picks up a random number after waiting that time, right? Random number of slots. So you can see that this is kind of a slotted mechanism, the carrier sense multiple access collision avoidance, okay? And within a contention window, okay? Contention window is the maximum possible random time that it can take, and wait before transmitting. So the reason for this is probably there are more than one node, as we mentioned earlier, waiting for transmission. So they try to randomize each other so they don't actually transmit at the same time. If there are transmissions by other mobile stations during this random time, so I waited for a random time, okay? And during that random time, I hear someone else transmitting. I don't count down the random time. So the mobile station, so if I picked a random time of, let's say, 3 seconds, first second passes and I don't hear anyone transmitting, okay? Second time passes and I hear someone transmitting, I'm not gonna count the third, okay? So after the second, I will stop the countdown. Once the transmission finished, I still have 1 more second to take, right? So basically, if I want to represent this, so here is my wait time, and let's say it is 3 seconds, okay? So second 1, second 2, second 3, and the total here is my wait, random wait, okay? And during this time slot, okay, so this is node A, it's waiting now, and this is node B, and somehow during time slot 2, node B was transmitting. So node A, when it's trying to count, okay, I finished my first time slot. The second time slot, someone is transmitting. So I'm gonna carry the second and the third until after this transmission finishes. So this is gonna be my second time slot. This is gonna be my third time slot, right? Shifted to, so I'm not counting down. I'm not counting the time where someone else is transmitting as part of the countdown of my wait time. Okay. Then picks up a random. So we said it will freeze its counter. It resumes counting down after the mobile station's finished transmission. And then after that, it will wait DIFS, and then the mobile station can start its transmission if there is no body over the medium. Okay, so what's the DIFS for? It's actually a way that allows higher priority types of transmissions to happen in this protocol. Here is what we mentioned earlier in the previous slide, shown on a time sequence diagram. So let's look at this. So we have mobile station A has a frame, has been transmitted. Mobile station B and C are sensing the medium, right? So let me point. So A is transmitting a frame. Mobile stations B and C are been sensing the medium because they have something to transmit, right? And then both of them, B and C, are gonna pick a random delay because they found the medium not available. Then mobile station A, for example, C is waiting for this whole duration, while mobile station B random time says wait until here. At the end of the wait of mobile station B, the medium is available. Nobody was occupying this, so it will start transmitting. Now, during that time of transmission, mobile station C is not gonna count down, so it will continue counting down after, even though its actual time has finished here, but it will continue further because it was not reducing its count time during the transmission of B. Then it will find that the medium is available, that's mobile station C, so it will start its transmission at this point, okay? So you see, okay, so it's still, right, still, just this shows you the different events that happens, which I described already, okay? Okay, further, why do we have this DIFS that I mentioned earlier? The reason for that is because we allow, again, this is another explanation of the methodology. So you have the DIFS duration and then the contention window, which is kind of like wait time for each one. Medium becomes busy, wait for DIFS, contention window, next frame, and so on. Why do we have those DIFS? Because if we have another higher priority transmission in a different mode of communication, then they will be able to capture the medium while all the other nodes using the distributed function are waiting. They cannot transmit during this wait time. Okay. Here is an example of the back-off interval and the introduction of the DIFS. So this one shows complete details of what I mentioned, including the arrivals of the different nodes, okay? I'm not gonna describe this step by step. You look at it, please. Try to understand how it works, and if you have a question about it, come back to me, please, okay? Few things that you can see here is that it shows you here when stations, so don't forget we have here like 4 stations shown in the time sequence diagram, and this shows you the arrival of packets, these arrows, just to understand what's shown here. And then this explains when a medium is busy. This explains when, so busy here, and this explains the back-off waiting delays of the medium as well, okay? So this figure is really very interesting. Looking at the figure and reading the text, you should be able to follow it as per the methodology that we described earlier, okay? Now, the random back-off time is not fixed, or basically the maximum random back-off time. Remember that you select a random time between a certain minimum value and a larger value. The mechanism in carrier sense multiple access collision avoidance allows that maximum value to increase depending on whether for a particular node, this is your first trial to transmit on the medium, or it's your second trial or third trial for the same packet. So if I have a packet to transmit, and I sense the medium, I find that the medium busy, I calculate my backup time, and my backup time is within a certain minimum and maximum value. Then the next time, let's say after the end of the backoff, I will find the medium busy, so it's not available for me. Then I will calculate another backoff. Now for that second backoff for the same packet, I have a bigger window, and the window increases in an exponential fashion. So it's multiplied by 2 every time. Okay, so every time you retry for the same packet, the window grows up until it reaches 255. That's like 256, but starting counting from 0. So that's 2 to the power 8 until it reaches 2 to the power 8. And then it doesn't increase after that. Okay, so that's called the exponential growth of the random backoff maximum allowable time. This way, nodes that are suffering from repeated busy medium, they give themselves more time so not to collide with others. Remember that this methodology is mainly meant to achieve something called collision avoidance. So you're trying to minimize the collision. Why? Because in the first place, in a wireless medium, it's very difficult to actually detect the collision when it happens. While on a wired, it's easier to do so. Okay? This shows you, remember I mentioned that DIFS, that wait time, is designed so that it can allow other types of transmissions with higher priority to take place. Example of those is, for example, the acknowledgements. So for those ones, if you are sending an acknowledgement of a packet that you have received, you will not wait for the long duration of DIFS. You will wait for a shorter one called the short IFS, short interframe spacing. And this one, shortest time, which means highest priority. So you give higher priority to things like acknowledgement. There is an intermediate one, shorter than this but longer than this, which is called the PIFS, the point coordination function. This is a method where the access in Wi-Fi is happening actually using a reservation mechanism. This is used to service things like voice and video where you don't want lots of variations. So it's no longer a random access method if you are working in the PIFS. And there is something called the extended IFS, and this is like a lower priority case than the regular transmission case, and it's used only in very, very special cases of the distributed coordination function to send frames with very low priority, things like network configuration frames and stuff like that. Okay. Okay, now there is a problem that can happen between okay, again, sorry, this slide is not talking about that problem. This is just talking about the acknowledgements, and as I mentioned, the acknowledgements are made sure to be transmitted with higher priority than the regular frames, and this is by the fact that they wait for SIFS only. So whenever a node has an acknowledgement to send, okay, that node, like the base station here, for example, is going to take the medium faster than anyone else waiting, because all the others waiting will have to wait for a longer duration. So imagine that they are waiting here, they have to wait until here, but by the time they can actually contend for the medium, already the acknowledgement has captured the medium because it has to wait for a shorter duration, SIFS. Okay. The next is the hidden terminal problem. This is the problem that I wanted to talk about in the 2 slides ago. That hidden terminal problem happens similar to the scenario that I described to you in the last lecture. You have node A and node B, both of them are communicating, sorry, A and C, both of them are trying to communicate to B. As you can see, A has a range of transmission that can send to B. C has a range of transmission, which is this green one, that can actually send to B, but both of them, they are out of range from each other, so they will never hear each other's signal. This means that whenever they are listening to the medium, whether A or C is listening to the medium and the other one is transmitting, they will never be able to hear each other. This means that they can always collide together all the time, because they can never, even when they are doing the backoff, since I can't hear the signal of the other one, I'm not gonna incorporate that as busy time, so my backoff is not gonna be affected by the transmission from the other one, right? That means that the whole mechanism for those two, they called, are hidden from each other because they don't see the signal of each other. And the mechanism of the carrier sense multiple access collision avoidance is going to be super inefficient in these cases. To avoid this, what we introduce, or what's introduced, is something called handshaking. So each one of them, instead of sending its long packet of information, it will send a very short packet to node B asking for permission to transmit. So it will send something like request to send. And then the one that reaches node B first is going to get a permission. So it's going to send get something called clear to send. If the other one now tries to send to node B, since node B has already given the clearance to someone else, it will not send it a clear to send. It will deny it its transmission. Hence, C will wait and assume that someone else is using the medium and will kind of deal with a back-off algorithm as if the medium is busy, while A will be able to send its packet. Now, that request to send, clear to send, RTS, CTS, is again high priority frame, very short frame. So whenever node A or node B are exchanging the RTS, CTS, they will use the SIFS, the short wait time, so they will get a chance to transmit that faster than any other one trying to transmit information, and hence it has higher chances of reaching its destination before anything else. That is the request to send, clear to send described here, as I described it already to you on the figure. And this is the request to send, clear to send shown on the time sequence diagram. And again, you see here that whenever you have request to send and that request to send is received by the other station, the clear to send comes immediately after, and then the data comes immediately after. This is just to guarantee that this will have priority over someone else who's trying to transmit, for example, so that you can clear the medium for transmission before someone else starts using the medium, okay? That's why it uses the SIFS around the clear to send acknowledgement or permission, okay? Also, we see that the acknowledgement of receiving the information comes. So this whole thing, from requesting to send until getting the acknowledgement, all these sequences, so request to send, clear to send your data, all of this, and then get the acknowledgement, all of this within SIFS. So that guarantees that they will happen in sequence without being interrupted by other transmissions from other nodes that might be waiting for the medium to become available, because all of those are going to wait actually a longer time, which is DIFS plus whatever their back-off window that they have calculated, okay? This is again the time sequence diagram in short format. Request to send, clear to send data, get acknowledgement. That's the typical sequence in carrier sense multiple access collision avoidance, and that's what we have in our access points that we see. Okay, again, even though we have done all of that, we'll still be suffering from some other problems similar to the problem of exposed terminal problem. So we have node A transmitting, right? And it is transmitting to node B. Node B is transmitting to node A, so those two can talk to each other. Now, if A and B wants to talk to each other and C and D wants to talk to each other, B being transmitting and in the range of C is gonna block C from sending anything to node D, but that's because of the reality of the wireless communication medium, so that's fine, should be fine. Even though the transmission of B is not gonna affect the reception at D, but again, because it's sensed by C, C is not gonna transmit. It's gonna avoid the collision. So that reduces the efficiency a little bit, but this is a problem that cannot be solved. It exists because of the wireless medium. At this point, we have finished this part on the medium access control protocols. A couple of quick announcements. Your midterm has been scheduled on the second week after returning from the Eid, so not the immediate week after the Eid, the week after. I'm gonna send you the exact date and update that on Blackboard. Also, you will have your assignment. I'm trying to actually finish all your recordings and post them for you as a support. Again, recordings are not mandatory, but I'm doing that to support you. So don't stop your study because of the recording. The only thing that have to wait to resolve right now is how we will handle the quizzes. I'm also gonna post for you the intermediate deliverables of your project. I wish you a safe time, accepted deeds at the end of Ramadan, and happy Eid, and see you after the Eid inshallah, and hopefully you'll be able to come back to face-to-face so I can see all of you. Best wishes of success, of happy time with family, of safety, and inshallah have a nice break. Assalamu alaikum.